Okay, now let us look at section 10.6, which is conservation of energy. Let us remember at first the kinetic energy for moving bodies. For the first one, if we have a block, its mass is m and the velocity is v. Then it is easy to remember that its kinetic energy, it's kinetic linear kinetic energy, which is equal to half mv squared. We know that. What if we have a rotated body? Its linear velocity is 0, its radius is r, and its angular velocity is omega. Okay, how much the kinetic energy? Look at this. For this example, we are talking just about this rotation up. The linear velocity is 0, but it is rotated with omega velocity, okay? So in this case, we just have the kinetic energy is rotational kinetic energy, which is equal to half in moment of inertia multiplied by angular velocity squared. This is the effective mass for rotated bodies, okay? This is the velocity for rotated body, which is the angular velocity. This is the velocity. Linear velocity is 0. It is not moving, okay? What if we have both of them? We have angular velocity and linear velocity for a radius r body like this, We have linear velocity and we have omega also, angular velocity. Then the kinetic energy will be composed of two parts, linear part and rotational part. So the kinetic energy will be equal to linear kinetic energy, which is half mv squared. It's the same like this one, plus we have another part of energy, which is half I omega squared. You need to remember that omega is v over r. Omega squared, v squared over r squared. And we can put it v squared over r squared in the place of omega in our equation here. Look here. The kinetic energy is equal to the linear kinetic energy plus the rotational kinetic energy. Omega is v squared over r squared. I is I, half is half. And just I multiply by m and divide by m. It is just 1. Okay? I need it. Because I need to get out from the parentheses or the bracket m half mv squared. Half mv squared. I can't take them out of this bracket. So the terms I have then 1 plus I, which is the moment of inertia, over r squared. R squared I. And half mv squared is out. So that I can write the kinetic energy for a rotated body in two ways. This is the first way. This is the second way. You don't need to carry them in your mind in the exam. We will give you them in the exam, and you need to use anyone you like. Okay? Look at now at this example. It is easy to understand the idea using an example. What if we have a block moving, sliding on a hill, then go on the horizontal level, no friction in this system. The mass is 5 kilograms. The first altitude h is 3 from the 0 level. Also, we have a ball, solid sphere. This is important. Sometimes we have sphere shell. We have cylindrical shell. We have solid sphere here. Its initial velocity is 0. And omega is also 0. At the first point number 1. This is point number 1. This is point number 2. And the mass is 5. It's the same. The altitude h is also the same. we need to know the radius because we have rotational motion. Okay, now if we need to calculate the mechanical energy, total mechanical energy for this system, the total mechanical energy is constant because we have just the gravitational force, which is conservative force. So we can use the conservation of energy. We know that the energy is equal to kinetic energy plus potential energy due to gravity. We don't have a spring here. If we have a spring, just you need to add the spring term. The energy at point number 1 here, it is not just a potential energy. It is the kinetic energy half mv square plus mgh. We know g. The velocity is 0. We don't have kinetic energy. The potential energy is 5, which is m, g 9.8, the altitude h is 3. Then the total mechanical energy is 147 joules, which is constant. Okay? Let us look at the rotational system. We have the mechanical energy is equal to kinetic energy at this point, at the first point, plus the potential energy. The kinetic energy is 2 terms, as we said before. It is a linear kinetic energy plus rotational kinetic energy plus the potential due to gravity. The linear is half mv squared. The rotational is half I omega squared at point 1 plus mgh1. V and omega are zeros. Then these 2 terms are zeros. Okay? The kinetic energy is 0 at the first point. The potential energy is mgh. M is 5. The same. The both bodies are the same mass. G is the same. The altitude h is the same. Then the mechanical energy for both systems are the same, 147 joules, which is constant. Okay? Now we see I here. We need to compute I to know it because we will use it later in the next part. I for a solid sphere. This is a solid sphere. I the moment of inertia for a solid sphere rotated. This rotation is around axis in the center of the rotated body. So we need to use the rotation around the axis for a solid sphere, this one, which is 2/5 mr squared. Okay? M is 5, R is 0.3 squared. We need it. Then the moment of inertia is 0.18 kilogram meter squared. So the effective mass for the rotated body is 0.18 kilogram meter square. Okay? But now we are at the first point, which have just the potential energy, and there is no any kinetic energy for 2 cases because the velocity or the angular velocity are 0. Then the potential energy is 147 in both cases, which is equal to the total mechanical energy, which is constant. Okay. Now at point 2, this is point 2. This is point 2. We have the altitude h now is 0. We don't have potential energy. And the body has velocity. We have kinetic energy. Let us look now. For the first block, the mechanical energy is equal to kinetic energy plus potential energy. Kinetic energy is just linear here, which is half mv squared plus mgh2. h2 is 0. Half m is 5. v2 squared, we don't know the velocity at this point. We need to find it. And the potential energy is 0. So the mechanical energy at the second point is equal to half 5 v2 squared, which is equal to the mechanical energy at the initial point, which is 147 joules. So v squared is equal to multiplied by 147 divided over 5, which is equal to 58.8 meter per second. All are squared because we have v squared. How much the velocity or the speed now? It is equal to the root of that number, which is 7.7 meters per second. Right? Okay. Now we have just kinetic energy at this point for the first system. For the second system, the second system at the second point here, we have rotation, we have moving body, we have velocity, linear velocity, we have omega. We don't have potential energy because h is 0. H, 0. Okay? The kinetic energy here, it is two terms, linear and rotation. Also, which is equal to half mv squared plus half I omega squared. And the second picture of that law, which is this one, I can use it also, which is equal to mv squared plus 1 plus multiplied by 1 plus I over mr squared. It is the same. Plus mg h2. H2 is 0. So the potential energy term is 0. I need to put the numerical values. Now half is half, m is 5, v is unknown, 1 is 1. I find it now here, which is 0.18. 0.18, it is I, over m is 5, the mass for this solid sphere, and r is 0.3. I need to square it, plus the potential energy, which is 0. This will be equal to half 5. This term is 1.4. This altogether is 3.5. V squared is equal to the total mechanical energy at first point. We know that it is constant. So V squared is 147 over 3.5, which is equal to 42 meters per second, all squared, because the velocity is squared. I am talking about the velocity. We don't have any omega now because we use the second form. We use this form, not this. In this form we have omega. This we don't have omega. Okay. The velocity is the square root of 42, which is equal to 6.5 meters per second. Look. The block which has energy the same as the energy of that sphere here, the velocity of that block is 7.7. The velocity of the sphere is 6.5. They have the same energy. Where is that velocity change go? Okay? You need to remember that we don't have rotational kinetic energy here. But here we have rotational kinetic energy. Some of the kinetic energy for the sphere is go to the rotation. So in this case, we have just velocity, linear velocity. Here we have two velocities. One is linear and the second is rotational. Both of them will be equivalent to this one. If we need to compute omega, it is V over R. V is 6.5, R is 0.3, which is equal to 21.6 radians per second. Now, I can tell you that kinetic energy here in the second system, which is equal to kinetic energy in linear plus the rotational kinetic energy, is equal to the kinetic energy for this system, which is just linear. Okay? But in this system, it divided to two terms, two kinetic energies. But in general, it will be equal to the total mechanical energy. That means the mechanical energy will be conserved in kinetic energy, even it was linear or rotational. Okay, you need to solve examples like this one. You can also, I will put another examples with spring or with without spring, but all have the same idea. You need to deal with linear kinetic energy and rotational kinetic energy. Thank you.